8.1 arc length. Your homework will be problems 9 through 19 odd. To begin, let's think of it as the sum of lines. What do we mean by length of a curve? We might think of filling a piece of string to a curve and then measuring the length of a string with a ruler. Well, the way we measure the length is by taking the sum of lengths of line segments. If it were a polygon, we are going to define the length of a general curve by first approximating it by a polygon, then taking the limit as the number of segments of the polygon is increased. Now, suppose a curve C is defined by the equation y equals f of x, where f is continuous and a is less than or equal to x less than or equal to b. I like interval notation when we think of that. We obtain a polygon approximation to C by dividing the interval AB into n subintervals with endpoints x1, x2, up until however number we need, xn, with an equal width of delta x, or change of x. If y sub I equals f of x sub I, then the point pi xi yi lies on C and the polygon with vertices p sub 0, p sub 1, all the way to pn, just like the image below. So we first labeled them as x, but really they can be any point. And so our hopes are that if we find the length of these subintervals, we can use that to find the length of our arc, or this curve in our function. We define the length out of the curve C with the equation y equals f of x, for a being less than or equal to x, less than or equal to b as the limit of length of these inscribed polygons, if the limit exists. The equation is L is equal to the limit as n is approaching infinity of sigma, with I being equal to 0 all the way to n, of p I sub 1 pi. The arc length formula. We can also apply similar ideas from the mean value theorem to use integrals for the arc length. So while this summarizes the idea of it, think of it of when you learned integrals and you use Riemann sums. We can create subparts to find the limit, but now that we know integrals, we can just use our arc length formula. So this is what this section is about. This is the formula we'll be using. The arc length formula reads, if f prime is continuous on the closed interval AB, then the length of the curve y equals f of x with the closed interval from a to b is L is equal to the integral from b to a of the square root of 1 plus f prime squared dx. Example 1. Find the length of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. All right, so just to have it handy as we work on this next problem, let's remember our arc formula. Our arc formula is our limits, our high and our lower point of 1 plus our derivative squared dx. Okay, and we're just write it down so you can have it handy as we work on this next problem. Okay, so we need two pieces of information for our equation. Really three. We need our limits, our highest above, and then our lowest. And then we need our derivative. Okay. Since we're working with dx, I need to look at my x's, x1, x2. So we have our equation, L equals from 4 to 1. The square root of 1 plus, okay, I need my derivative squared. Let's go ahead and find our derivative. Well, we want it in terms of x, so let's go ahead and get y by itself. So let's solve for y. So we have y squared equals x cubed. We take the square root of both sides, so we're left with y is equal to the square root of x cubed. Let's write it as a rational exponent, so x raised to the 3 over 2 power. Now that we solved in terms of x, let's go ahead and take the derivative. Y prime is equal to 3 over 2x, and then 3 over 2 minus 2 over 2, we get 1 over 2. Okay, let's write that into our formula. So we have 3 over 2x squared. All right, let's go ahead and use our arc length formula to find our arc length. So we have L is equal to the integral from 4 to 0, 4 to 1, of the square root of 1 plus, and we're going to square everything inside, right? So that square applies to everything. So that gives us 9 over 4x squared dx. That was supposed to be a 1/2. So it's not a square. It's 1/2 times 2 just gives us 1. So it's just an x. Okay, let's go ahead and integrate. This one isn't so bad. We can just go ahead and use our u substitution. So we can let our inside be u. So u is equal to 1 plus 9 over 4x. Therefore, partial derivative du will just be 9 over 4 du. Let's go ahead and also think about our limits. Let's change our limits. So when x is equal to 4, let's plug in 4. We go ahead and get 10. So when u is going to be 10, and when we plug in 1, we get 13 over 10. 13 over 14, I'm sorry. All right, let's go ahead and continue. So what do we have now? We have the integral from 10 to 13 over 14 of the square root of u du. And because our du has a 9 over 4, to compensate, we're going to write 4 over 9. Let's go ahead and integrate. So we have 4 over 9. Once we apply the integral, we have u to the 1/2 plus 2 over 2. We get 3 over 2. Divided by 3 over 2 gives us 2 over 3 of 10 and 13 over 14. All right, let's go ahead and work that out. Let's do that algebra. So we plug those values in. I'll leave that 9 over 4 on the outside. I'm sorry, 4 over 9. All right, let's go ahead and plug in 10. To avoid making a silly mistake, I'll go ahead and try to color code. All right, we'll plug in 10 for you. We're left with 2 over 3, 10 to the 3 over 2 power. And when I plug in 3 over 14, we're left with 2 over 3, 13 over 14 to the 3 over 2 power. We see we have this in common. Let's go ahead and factor that out. So that we factor out a 2, 2 times 4, we get 8, 3 times 9, we get 27. And let me write it as a radical. Maybe that would make more sense to us. So instead of 3 over 2, I'll write it as the square root of 10 cubed minus the square root of 13 over 14 quantity cubed. All right, I could take out 2 of those 10s out. So I can have 10 square root of 10 minus we have forget my notes. I've been writing this wrong the whole time. It's 13 over 4. Why was I writing 14? 13 over 4. 4. Okay. So I can take the square root of 4, which gives me 2, and 2 cubed is 8, so we're left with 1 over 8, and the square root of 13 square root of 13. All right? We can get rid of that denominator of 8 by multiplying in that 8 into both, so that we're left with 1 over 27, 80 square root of 10, minus, that cancels that 8, 13 square root of 13. And that's our answer. I'm sure you would agree. The formula is not so bad. And as always, the algebra is what becomes a challenge. Okay, now for this problem, we worked in terms of x, but really our equation can extend to work also in terms of y. With arc length, we're also able to interchange the argument. We may also interchange the argument of our functions if that will produce an easier function to work with. And when we're talking about what's better to work with, we're talking about integration. What's easier to integrate with? Because not all problems are easy. If a curve has the equation x equals g of y, where c, d are in the closed interval, and g prime of y is continuous, that's always important, then by interchanging the roles of x and y, we obtain the following formula for its length. So our length is our integral from d to c of the square root of 1 plus our derivative in terms of y squared dy. So in other words, when you work with these when you solve for x. You have x equals that's solved, and you're working in your y variable. Let's do an example. Find the length of the arc of the parabola y squared is equal to x from 0 to 0, 0, 0, and 1, comma 1. All right, we see here that we are in terms of x. I'm sorry, terms of y. Meaning x is the one that's by itself. Because that's the case, it might be worth our effort to integrate in terms of y. And if that is also the case, then our limits of integration will be our y's. So our equation would be from 1 to 0, the square root of 1 plus our derivative squared in terms of y. Let's find our derivative. So we have y squared equals x, or maybe it might be easier to write x equals y squared. Let's go ahead and find x prime, our derivative, which is just 2y. Okay, if we go ahead and square it, we're left with the integral from 1 to 0, the square root of 1 plus 4y squared dy. Now, we have learned so many integration techniques. This one we see would fit our trigonometric form of integration, right? We have 1 plus something squared. All right, because we have a plus, this fits the format so that we have y will equal 1/2 tangent theta. Remember, our whole purpose is to get 1 plus tangent squared theta, so we can use secant squared. If that's y, then our partial derivative dy will be 1/2 secant squared d theta. And always remember, so we don't forget, when we're using trig substitution, we have to use our triangle to find our remaining pieces in terms of our variable. In this case, it'll be y. Right? So with that said, if y equals 1/2 theta, then we multiply it by 2. So we have 2y equals tangent of theta. We can write it as over 1. Tangent is opposite over adjacent. So opposite of theta will have 2y. Adjacent will have 1. Our hypotenuse will be 4y squared. 4y squared plus 1. All right, and this is just our setup, so we don't forget to find those values. Let's go back to our integral. All right, so we have the square root of 1 plus 4, and we have that y squared. Our y, we said y is 1/2 tangent squared. Let's clean that up. So this gives us the square root of 1 plus 4 times 1/4 tangent squared theta. So we now have 1 plus tangent squared theta, which is the same as secant squared theta. So we now just have secant theta. Let's replace that into our integral. So we have our integral from 1 to 0. And in the radical, we're going to have, that's now replaced by a secant theta. In our dy, we said dy is 1/2 secant squared d theta. Okay, let's go ahead and continue to integrate. Let's pull out that 1/2 constant. We have secant cubed theta d theta. Okay, this is a problem we've seen before. To save time, remember that to integrate, you have to use integration by parts. And we actually did this example. If you go back to section 7.2, example number 8 from your textbook, or I don't remember what example is from our notes, we have this exact problem in our notes. So we're going to use our conclusion. When we worked this out, we saw that our answer was 1/2 times secant theta tangent theta plus the ln of secant theta plus tangent theta, absolute value. All right, so now we managed to integrate. Now we have to replace all of these theta arguments in terms of our variable. In this case, it's a y. So I need to find the value of secant and tangent. All right, secant theta. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So we want hypotenuse over adjacent. So we have the square root of 4y squared plus 1 over 1. And tangent is opposite over adjacent. So 2y over 1. So basically, we can disregard that over 1. Okay, let's make that adjustment. So that we have 1/2 times 1/2, that's just 1/4. And we have, instead of secant theta, we're going to write the square root of 4y squared plus 1. So tangent theta, we're going to write 2y plus the ln of the absolute value of the square root of 4y squared plus 1 plus tangent theta, which is just 2y. And for all of this, our limits, what is our limits? Our limits are from 1 to 0. Okay, let's go ahead and work this out. So once we plug in 1, we get when we plug in 1, we get the square root of 5 times 2 plus the ln of the square root of 5 plus 2. That's our first one. Minus, when we plug in 0, we get 0 plus the ln of 1. And the ln of 1, that just gives us 0. So that we have 1/4 to the square root of 5 plus the ln of square root of 5 plus 2. Let's clean that up. We can multiply in that 1/4. So we're left with square root of 5 over 2 plus the ln of square root of 5 plus 2 over 4. Now you punch into your calculator, that's about 1.478943. Again, don't forget the integration we learned in chapter 7. It's really important as we move for maybe the next 2 chapters, and then after that we kind of move away from integration. Okay. Because of the presence of the square root in the formula, the calculation of arc length often leads to an integral that's very difficult or even impossible to evaluate explicitly. Thus, we sometimes have to be happy with just an approximation of the length curve. To use this and answer this next example, we used methods learned from section 7.7. But because of the summer course, we skipped that section. But I want you to know that there's a different way of approaching it. And essentially, it's similar to Riemann sums. Essentially, we divide it into subparts and then add the sums. We're not doing that for this example. Let's move forward. The arc length. We will find it useful to have a function that measures the arc length of a curve for a particular starting point to any other point on the curve. Think of this as creating a formula. Thus, a smooth curve C having the equation y equals f of x with the closed interval ab, let s of x be the distance from C along C from the initial point P sub 0 a, comma f of a to the point Q x, comma f of x, then s is a function called the arc length function. S of x equals the integral from x to a of the square root of 1 plus f of t squared dt. And we use t and not x or y's because it may vary, right? We've learned we can use x's or y's. In general, we can create a general formula to find the arc length as we set our integral limits. So essentially, we can have our own special formula where we have our upper bound being x, and whatever your starting number is, your initial number, that's the number you're going to actually put in. So that may vary. It is helpful if we focus on the integrand first. So if you want to, you can set it as in terms of x or in terms of y, but remember you still have to take the derivative. Don't forget that that stands for derivative, and we see it in that fraction form. That's your Laban's derivative. Just a different way of writing it. So we see that, remember, the top one is what it's equal to. The bottom one is in terms of. And you see that a lot as you work in, for example, Calculus 3, this type of notation. Don't let that ever throw you off. First, top one is your formula, like an f, if it's equal to f or y. Your denominator is your variable you're working with. Okay, let's do this next example. Find the arc, the arc length function for the curve y equals x squared minus 1 over ln of x, taking p sub 0, the point 1 comma 1 as the starting point. Okay, so we know our starting point, but we don't know the ending point, so we'll just let that be x. So that our formula will be, it starts from 1 and goes all the way to x. Remember, the starting number goes on the bottom. Now let's write our formula. So we have the square root of 1 plus our derivative. Let's find our derivative. Y prime is 2x minus 1/8 times 1 over x. You can clean that up to be 2x minus 1 over 8x. All right, so that's going to be our quantity squared. Let's go ahead and work it out. Let's start off by squaring it. So we have the square root of 1 plus. So this is a type of binomial, right? So remember your binomial rules. If we're squaring it, if we have a plus b squared, the same as a squared plus 2ab plus b squared. So that's going to give us 4x squared minus 2 times 2x times 1 over 8x plus 1 over 64x squared. It's much quicker than FOILing, so I just wanted to remind you of that. All right, let's go ahead and clean that up. So that's our 4. So we're left with 2. Our x's cancel. We're left with 1 plus 4x squared minus 1/2 plus 1 over 64x squared. Let's go ahead and combine like terms. So we have 4x squared plus 1/2 plus 1 over 64x squared. Now, we have to be careful. Our trinomial is actually a perfect square trinomial. So we can write it as a quantity squared. This factors to be 2x plus 1 over 8x squared. Lucky for us, isn't it? So therefore, our square and our radical are inverses, and we're left with our integral of just 2x plus 1 over 8x dx. So if we go ahead and integrate, okay, let's go ahead and integrate so that we have t squared plus 1 over 8 ln of t, with our limits being x and 1. Let's go ahead and plug those in. I'll be extra careful. So we have x squared plus 1 over 8 ln of x minus our lower, which is 1 squared plus 1 over 8 ln of 1. And ln of 1, that is 0. In case you forget, remember that's e, base e. So that means e to what power gives us 1? It has to equal 0. Okie dokie. So we're left with x squared plus 1 over 8 ln of x minus 1. And we have created a general formula to find the arc length. All we need is an ending point. All right, that was it for section 8.1, arc length. I hope you enjoyed it. Thanks.